Okay, we're going to look at rates of reactions. So let's look at the units of molarity. That's going to be moles over liters. So when we use these brackets, we mean molarity. So this means molarity of A. So what are some of the ways that you can speed up a reaction? You can increase the concentration of the reactants. You'll have more molecules to hit each other. You can increase the temperature. The molecules will have more kinetic energy and be moving faster. You can increase the surface area of reactants if you have a solid, and you can use a catalyst. So let's look at a definition of a reaction rate. We're going to be using typically molarity per seconds. So you can type it out this way. This means molarities per seconds, or you can put molarity on top over seconds. Let's use this balanced equation as an example. So we have 2 nitrogen dioxides going to 2 nitrogen monoxides plus oxygen gas. So these are our reactants. These are our products. If you were asked what is the rate of oxygen production, you would set it up as the change in concentration of oxygen over the change in time. Delta O2 over delta time. If the time interval is very short, the equation gives the instantaneous rate. Otherwise, it gives the average rate. So let's say you were given some data that at 5 seconds, it was 0.0050 molarity, and at 10 seconds, it was 0.0080 molarity. You would calculate your rate to be 0.0006 molarity per second, and that would be an average rate between 5 seconds and 10 seconds. Technically, this is not a short enough period to be an instantaneous rate. It's the rate between 5 seconds and 10 seconds. So what if we were asked about the rate of decomposition of nitrogen dioxide? It would be delta, concentration of nitrogen dioxide, over delta time. So here we have some data. At 0 seconds, it's 0.041 molarity. At 5 seconds, it's 0.031 molarity. So our rate is a minus 0.002 molarity per second. We have our rate between 0 seconds and 5 seconds. So we have more data. We have the data that at 10 seconds, it's 0.025 molarity. So we calculate our rate between 5 seconds and 10 seconds to be 0.0012 molarity per second. So note it's customary to work with positive rates. So how would you make these rates positive? You can either take the absolute value of the rate or the negative of the numerical value. Let's look at how data could be set up. You could have a table like this. So the table would give you the time and the corresponding molarity. So the question is asking, what is the rate of production of oxygen gas over the first 5 seconds? So at 0 seconds, it's 0 molarity. So we have 0 seconds, 0 molarity. At 5 seconds, it's 0.0050 molarity. So at 5 seconds, it's 0.0050 molarity. So this is the rate of our oxygen gas production over the first 5 seconds. Okay, so let's compare the rate of the decomposition of the nitrogen dioxide to the rate of production of oxygen gas over the first 5 seconds. Okay, so this was the rate of our decomposition of nitrogen dioxide. We're going to take the absolute value of this. So we put this on the top. So this was the rate of production of oxygen gas over the first 5 seconds. Put that on the bottom. And then we get 2. Does this make sense? Yes, it does, because we lose 2 molecules of nitrogen dioxide every time we make 1 molecule of oxygen gas. So it corresponds to our stoichiometry, so it makes sense. Okay, let's look at how we could graph our rate data. So we can make a graph. It could look something like this. So here's our time, and this is a longer amount of time. And there's our molarity. And notice it's times 0.0001 molar. That's just to make the numbers easier to deal with. Okay, so this particular question is asking for oxygen gas over the first 600 seconds. So we're going to have to estimate here. 600. Okay, well, this is halfway between 0 and 1,000 would be 500. So it's going to be somewhere here. So what we could do is we would get a ruler out and we would make a tangent line here. I don't know how nicely I can draw this. Be a straight line. Whoa, it's supposed to be a ruler. It's supposed to be a straight line. Okay, well, just assume that's straight. We would take a ruler and do a straight line at 600 seconds. So we're going up here and then making a tangent. And then we would take the slope of the tangent line. If you use a ruler, it's going to work out much better. And we would get some data points. I guess I can draw a line. Oh, look at that. There we go. There's a better line. So what you're doing is you're picking your 600 seconds and then making a tangent line close enough. And then you're getting the slope of the tangent line. So in this particular example, these are the data points that I got, which would be the slope of my tangent line. And then it was asking over the first 600 seconds. And so that would be from 0 to 600. So this is my average rate over the first 600 seconds. So now we're asked about the rate of production of oxygen at 4,000 seconds. So 4,000 seconds, that would be right here. So we would go up at 4,000 seconds. We would hit our line. And then we would have to make a tangent line at our 4,000 seconds, much better. And we would get the slope of our tangent line at 4,000 seconds. The data that I got was 0.0008 molarity at my data points was 5,150 seconds. Because remember, you're taking the slope of this line. You take the time, you go straight up, you draw a tangent to that curve. Because this is curving. If you notice, this is not linear. This is definitely curving. So that was the data that I got. I ended up getting 6.89 times 10 to the minus 8 molarity per second. So depending on how well you draw your tangent line, you might have slightly different values, but it should be close enough to my data. And this is an instantaneous rate. So we would do the same thing at 5,000 seconds. We would go up at 5,000 seconds. Let me get my straight line. So at 5,000 seconds, we would go up until we hit the curve. Then we would draw a nice tangent line at the 5,000 seconds. That looks good. And then we would get the slope of that tangent line. That would be an instantaneous rate as well. And the data that I got gave me 2.94 times 10 to the minus 8 molarity per second. So when you have to use a tangent line, you're obtaining the instantaneous rate. Okay, so now we're going to look at relative rates. This is a combustion reaction. So combustion means plus oxygen. You are going to have to be able to balance your equations. This is given to you, but normally you will not be given balanced equations. You could just be asked the combustion of propane, but I would give you the formula for propane. So we have to use our stoichiometry here. And the question is going to ask you about comparing the rates. So what you do is you always take the reactants as negatives because you're losing them. So that's why there's a negative here and there's a negative here, because propane is a reactant, oxygen gas is a reactant. You put delta and then the concentration of the reactant on top, and then this is your stoichiometry. You put that on the bottom. Again, with the stoichiometry, put that on the bottom. And then the products will have positive values because you're making products. So again, you would use your stoichiometry, put that on the bottom, and your stoichiometry for the water or the steam, put that on the bottom. So now we have an equation. So what this means is that the rate of propane is 1/2 compared to the rate of losing oxygen is 1/13 compared to the rate of making the carbon dioxide compared to the rate of making the hydrogen, the steam. So this is now all equal, and then we can do lots of different kinds of problems from it. So it all starts with the balanced equation. And then when you're doing relative rates, you set it up using the balanced equation in the stoichiometry. Okay, so now we have a question. At a particular instant in time, the value of the decomposition of butane is 2.0 times 10 to the minus 3 moles per liter a second. What is the value of the formation of steam in that instant? I believe I called this propane earlier, but this is butane. Okay, so in this case, what we're doing is we're only using the parts that we need. So we need butane. This is our butane. That's our rate. So we put that here. And we're comparing it to the steam. Here's our rate for the steam. We put that here. And this particular problem is only asking about the decomposition of butane compared to the formation of steam. So we don't need to worry about the other parts. Okay, once you have this, you have an equation. We can rearrange the equation and get the values all on one side. And so that tells us that our formation of steam is equal to this setup. Now we were given the formation of steam. That was the, let me get rid of this. That was this value here. Oh, wait a second, I'm sorry. We were given the decomposition of butane. That was this value here. Okay, so we were given this, the decomposition of butane. So we take our decomposition of butane, we put it in here, and then we use the numbers that we had, was a negative 10/2. We use those as is, and that gives us our formation of steam at that instant. So this is what we're trying to find, and that's what we solved for. So we have to look at what was given, which in this case is the decomposition of butane. Here's our decomposition of butane. And what are we trying to find? The formation of steam. And that was this one. Okay, so now we will start with some rate laws. Okay, we're going to study the forward reaction. That's just to simplify matters. So if we were to write the decomposition of nitrogen dioxide gas, this is the same one we've been looking at, and we were asked to write a rate law for the decomposition of nitrogen dioxide, we would say that rate equals K, lowercase k, concentration of nitrogen dioxide to the power of N. N is the order of the reaction. K is called the rate constant. So most commonly, you're going to see the N is 0 or 1, which is called first order, or 2, which is called second order. Now, these are the most common. They're not the only. There's other orders, but these are the ones you're going to see the most often. So if you were asked to write a rate law for the decomposition of nitrogen dioxide in terms of the production of the products, we would have to look at our products. So we would say rate equals some rate constant, nitrogen monoxide to the power of Y, oxygen gas to the power of Z. And the Y and the Z are exponents, and they are determined experimentally. So in other words, you have to do experiments and get data. So how can you do these experiments to determine the rate laws? You need to see something. So the most common way is to measure the appearance of a product that can be determined by measuring its absorbance. This is an extremely common method of determining the products and then the rate laws.